Alrighty, hi y'all. How's everyone doing today? Thanks for joining in. Oops, sorry. Go back. I hope everyone is doing well and they feel prepared for the exam. This hour is just to answer any last minute questions that you may have. Did anyone go to Dr. Lindahl's review session before this that you still have questions about? Did you find his review session helpful? Or you can use the chat and you can let me know something that you want to see or go over, if anything that you have questions on, and you can unmute yourself, anything like that. This hour is yours to just ask questions. Whoever's speaking can go.
Can you specifically go over, I think it was number 8 from the sample exam?
From the practice exam? Yeah.
Mm-hmm.
Yep, so it's going to be this one here. So this one is very similar to just finding like the order of a reaction. The thing that you want to look for when you have more than one reactant or even more than two reactants is you want to look for two trials in which the reactant of interest is changing concentration and then the other ones are being held constant. So if we look at NO2 right here, we want to look at the 6 trials that are performed and we want to find a time. If we're looking for this one to find the order, we're looking for it to change while the other ones are staying the same. So right here we have it going from 0.001 to 0.002. And if we look at if we look at fluorine, that's staying at the same concentration. And then the NO2F is also staying at the same concentration. So 1 and 2 is a good trial if you want to find the order for NO2. So what trials would you use if you're looking to find the order for F2 in that case?
The 3rd and 4th?
Yep. So we said this one was going to be for NO2. So then 3 and 4 would be good for F2. All right, if we look at NO2 again, we don't want to do it from 0.002 to 0.006 because F2 is changing from 0.005 to 0.002. And NO2 is changing, or NO2F is staying the same. So we don't want to use this one because now 2 factors are changing. And so we can't directly tell if the rate is changing based off of the NO2 or of the F2. Okay. So then what would be the trials that you want to use for NO2F?
I guess 5 and 6 after that.
Yep, you would use 5 and 6 for that one. NO2F doesn't really matter too much, I think, because it's going to be a product, but it's still something that we can look at and we can still consider. So when we're looking at, we want to find the rate constant for this reaction. So we have to look at their R reactants. Our NO2F does not matter because this is a product. Okay, but we can still go through the same motions to give you an extra practice of what that would be. So if we're looking at NO2, we're looking at 0.001 to 0.002. What do we do to 0.001 to get to 0.002? By what factor?
Double it?
Yep, we double it, right? To get from here to here, we times 2. So what happens to the rate in this case?
It's being multiplied by, it's also multiplied by 2.
Yeah, awesome, right? So this is also multiplied by 2. So if our concentration is going up by 2 and our rate is going up by 2, what would be the order?
First.
Yep, so this would be first order. Okay, and then how about for F2? What is it going from 0.002 to 0.004?
It is, I mean, it's doubling, but since the rate is also doubled.
Yep, this is times 2,
Yeah.
and this is also times 2. So what order is this one?
Also first.
Also first order, awesome. Okay, so if we were to write the rate law for this reaction, we would say the rate is equal to what comes first in a rate law?
The constant?
Yep, the constants, we have K. And then we'll do we need reactants and products, just reactants? What goes onto our rate law?
Just reactants.
Just reactants, yep. So we'll have NO2 and F2. And do either one of them need an exponent?
No.
Nope, they do not. Right, because they're both first order. So overall, what is our order?
Second.
Good. Okay, so now we can use any trial that you want in order to plug in for the rate, that concentration of NO2 and the concentration of F2, and then you can solve for K. What units are we expecting from K before we even solve for it?
Units would be 1 over concentration times time.
Yep. Yep, so in this case, it's going to be molarity over second. So which answers can we immediately get rid of?
B and A.
Yep.
Oh, D and D as well.
Right, so we're expecting our answer to be C, right?
Yeah.
So what you can prove to yourself here is that you can say, okay, let's use trial 1. We can plug in our rate is 2.0 times 10 to negative 4. We don't know K, so that'll stay K. We have 0.001 and 0.005. And then you can solve for K and see if you get that 4.0 times 10 to the 1. Okay. Does that help you solve that one?
It does. So like if we're given a chart like this, we could just ignore the products entirely.
Yep. If you wanted to check that, right, this one, you would use 5 and 6. This goes up by 2. This goes up by 0. So it's like technically 0 with order, and it would get rid of itself, or like it would cancel out. It would just be 1 in your rate law anyways, and it wouldn't even matter.
Thank you.
Of course, if you wanted to solve this, like how we solve the one from the homework, you can do, right, your rate 2 is equal to K. You have NO2 to the M, and then F2 to the N. You could do this, and you could do the same thing that we did for trials 2 and 1, but you would put them over each other. So it would be 0.00, oops, sorry. You could say that you have 4.0 times 10 to negative 4, K, 0.002 to the M, 0.005 to the N, all divided by 2.0 times 10 to negative 4, K, 0.001, and this one. And you would still get the same answer. You would find that N is equal to 1 here. Or I'm sorry, that M is equal to 1 here. And then that would just confirm your answer at the top. Okay, does that help with question 8? Any other questions on question 8? Awesome. Okay, what do we want to see next?
Can you do question 2 on the practice exam?
Yep. Okay, so for this one, we have the average osmotic pressure of blood is 7.7 atmospheres at 25 degrees Celsius. We want to know what concentration of glucose, which is not ionized, would be isotonic with blood. So what is the equation, or what are we doing here? What do we need to know?
The equation is pi V equals nRT.
Because what type of problem is this?
Osmotic pressure.
Awesome. Yep, it's osmotic. It's an osmotic pressure question. So what are we solving for? What units are we looking for?
We're solving for n, right?
Yes and no. It's not, n is not the full thing that we need.
Then I don't know.
So can anyone help him before I answer?
Since we're looking for the concentration, that means that it's going to have to be molarity, I believe. So it'll be your moles over V. So and we're looking for N over V.
Awesome, perfect, right? So we're looking for a concentration. In our question, it's telling us in capital M in molarity. So we're looking for moles over liters, which would here be N over V. So we need to manipulate our equation so that we get N over V. Okay, from our question, what is our 7.7 ATM?
That would be, hold on.
Yep, what does it relate to in our equation?
You know, honestly, I don't know.
That's okay. Can anyone help him? All right, so it can't be N, it can't be V. What is 25 degrees Celsius?
Well, that's T.
That's T. So we're left with pi and we're left with R. Do we know what R is?
Yeah, 8.314.
So this one is actually going to be the 0.08.
Oh, yeah.
Yep, because this is in liters per 8 or times ATM over mole Kelvin.
Right.
And since we're in, this will have to, temperature will have to change to Kelvin. So that only leaves that 7.7 ATM is pi here. That's going to be our pressure.
Oh, okay.
And ATM is always in pressure units, and we changed that P, right? We usually see Pivnert. P becomes pi here when it's talking about osmotic pressure.
Oh, okay. That's what was confusing.
Yes. Yep. So we essentially have everything that we need. The ATM matches the ATM. The only thing that you need to do is change the 25 degrees Celsius to Kelvin. Does anyone know what 25 degrees Celsius to Kelvin is?
It's 298, I think.
Yep, perfect. Okay, so then you can just plug and chug there. If you want to rearrange your equation first, you have pi v is equal to nRT. You can divide by RT to get n by itself, and then you can also divide by v at the same time. And so you get pi over RT is equal to n over v. And then you just need to solve for that left-hand side of the equation. So we can do that by saying 7.7 ATM divided by 0.082 times 298. I didn't put all of my units in, but I showed you what they were before. And so N over V should be 0.31.
Okay, thank you. That helps a lot.
And then this is just a reminder that your units for this is in moles over liters, right? So you can get, you don't have to always stop at concentration. You can go a little bit farther afterwards if need be. Okay. The only question I had. Yep. So Maria asked a question about the Arrhenius equation with 2 in the log form. So your Arrhenius equation, when you have 2 K values and 2 temperatures, is going to look very similar to an equation we used last exam, where it has like the 2 in the natural log and then the 1 over temperature or something else. So this one is the ln of K2 over K1 equals, does anyone know what it equals on the other side?
Positive energy of activation over R, and then open parentheses 1 over T2 minus Actually, it'd be T1 in this instance because K2 is over K1. So it'd be 1 over T1 minus 1 over T2.
Yep. So that was perfect here. It does not matter whether you put K1 or K2 on top in your ln. The only thing that matters is that they are opposite with your temperatures. So this is the same equation. It does not matter how you write it. You just need to make sure that T1 or whatever's on top here is your furthest right temperature, right? So you have to go 1, 2, 2, 1, or you have to go 2, 1, 1, 2. As long as you know this, you should be able to solve any of those questions. And one thing you always want to check for is if temperature is increasing, what do we expect K to do? What should the value of K do if temperature is increasing?
I'm not sure, but I'm going to guess since no one else will say anything. Would it increase?
It does. Yep. Right. The more energy that your molecules have as temperature increases, the faster your rate of reaction will happen. Okay. And so if your rate is increasing, that means your rate constant has to be increasing. If temperature is increasing, K will always increase. You cannot decrease K as temperature is increasing. Okay, so I say this because if he's saying solve for another K, right, or he's saying solve for another temperature, and you have K is equal to 1, K1 is 1, and K2 is 10, right? You should expect that your temperature should maybe be 298 and then something higher, right? It should be 355, right? It doesn't really matter. But you should expect your lower values to be to be related to each other and your higher values to be related to each other. If you do all of this math and you say that your higher temperature now has a lower K than before, then that should trigger a red flag and say, I did something wrong. Let me go back to my equation and see if I plug this in correctly. Okay. I don't understand. What do you mean they have the values in different orders?
Okay, so for Fatma's notes,
Yep.
her combined Arrhenius equation, she has natural log of K1 over K2 equals EA over R times 1 over T1 minus 1 over T2 instead of having it like the other way.
So that just might have been a mistake on her part, but it should definitely be like 1, 2, 2, 1. If you do it the other way, you probably will not get the right answer. If you do get the right answer, then maybe everything that I've known is wrong. That would be a good thing for you to check maybe after this, if that is if you still get the correct answer, doing it K1, K2, and then T1, T2, but I think I've known that it's been K1, K2, T2, T1. That's always how I remembered it. And I have had success solving questions this way. So I would personally stick with the opposites, but if you want to check the IAs or the SIs way too and see if you get the same answer, I'd be happy to know that is also a correct way to do it. Then I don't have to emphasize this as much, but I'm pretty sure it has to be opposites for both of them.
Thank you.
For these two equations, in what situation would you use like either or? Because it's like the same one, but
Yeah.
I'm a little on that, sorry.
Yeah, no, it's okay. I just wrote them down because some people like to have K1 first on their natural log, and some people like and go 1, 2 because they like to go in order, and some people like to have like a higher number over a lower number. Whatever, you only need to memorize one version of it. It's just whatever you like to look at better.
So it doesn't necessarily make a difference in the outcome.
Nope, as long as they're opposite, right? As long as you have 2, 1, 1, 2, that's fine. And you have 1, 2, 2, 1. As long as you just remember one of those equations in red, you should be good to go.
All right, so then, but it'll give us the same answer no matter which way we do it.
Yep.
Okay.
So by 1, 2, 2, 1, I mean you have 1 here, 2 here, 2 here, 1 here. So I'm just like going like an L across the equation. 1, 2, 2, 1. That's just how my brain works and remembers it. Yes. I'm a visual learner as much as possible. Or if there are visual learners, I try to give you something to look at too. Okay. Yes. So do you know what slides number those are at? Well, it doesn't really matter. Okay, so if we're looking at like transition states and mechanisms and stuff, what can someone tell me what a transition state is?
Isn't that like an yeah, sorry, I was about to say like an intermediate phase, but that's kind of like not the right word since there's also intermediate states. So a transition phase would be, sorry, it just sounded like somebody died outside. A transition state would be like oh, what would like say like our C or C carbon 1, hydrogen 3, chlorine 1. The transition state would be where the carbon is kind of losing some bond with the chlorine, and the fluorine atom is starting to gain a bond.
Yep. So, right, a lot of the times we look at like your tetrahedral shape changing the way that it is positioned. So sometimes we'll see like carbon here, and then we'll have a chlorine, and then it'll be hydrogens like this. And your transition state is the point where another molecule has some bond with the carbon and some bond with the chlorine, and then also some full bonds with the hydrogens, because those are going to stay. So this here is the transition state. It's where we make and break bonds. Okay, this is where making and breaking bonds happens. Okay, it's not a stable state. You can never isolate the transition state. It always it has to go through this, but it can't exist as this. It'll only exist as a reactant, a product, or an intermediate. So this is like a transition state is like an in-between, where an intermediate that might be spelled wrong, but that's okay. How can you describe an intermediate?
It's stable.
Yep. So this would be a stable state. We'll call it before the final product. Okay, your transition state is what happens at the top of the activation energy. Okay, you need activation energy to get to your transition state. Once you get to your transition state, that's when it can then fall to your products or fall to your intermediate. Okay, so did he have y'all graph these at all, or kind of interpret a graph from them?
Yes, he did. He did show us a graph, one with the dip and one without the dip.
Okay, so if we had something that looked like, something that looked like this. How many transition states do we have?
Only one, I think. Just the one dip, I believe, is a transition state. Or is it?
The one dip is important, but it's not a transition state.
So that would be the intermediate state.
Yes.
Yeah,
So we
okay.
have,
We have 2 transition states and then 1 intermediate.
yep, so here and here are transitions. This is your intermediate. Okay, it's stable when the reaction falls down, right? It has to be some sort of endothermic and some sort of exothermic reaction, and that little dip is where it is a intermediate. At the top of your activation energy, that's where you have a transition state. Overall, what is this reaction? Is it endo or exothermic?
I'm gonna guess endothermic.
Yep, that's perfect. This is endothermic. Okay, to whoever asked about transition states and stuff, does that help with the charts? Yep, okay. Okay, let's go to the end of the exam where I have actually. Okay, so someone asked about memorizing equations, and then someone asked about what equations we need to know. So I'm going to turn to you and say, what are some important equations that y'all have used during this module that you think are important for the exam?
Arrhenius.
Yep, okay, so we have the Arrhenius, and what is the Arrhenius equation?
The Arrhenius equation is approximately A is equal to A times E to the power of negative activation energy over RT. That is one form. Then there's also the logarithmic form, which is the natural log of K is equal to the natural log of A minus the energy of activation over R time or over RT.
Did I write that?
There's also the combined form, which is, do you want the combined form? Yeah. Okay. The natural log of K1 over K2 is equal to energy of activation over R times 1 over T2 minus 1 over T1.
Awesome. Yep.
For the first equation on the left side, isn't it supposed to be a K there?
This one here.
Yeah.
I might have heard A when you said K, so.
Oh, sorry.
Yep, that looks good to me. Any questions on the Arrhenius equations in their various forms? Most of the time you can work with this one or this one. I think those are the easiest to work with personally. I know that there's an ln in there, but you don't have to take the ln later. So it just does it for you in the beginning. Okay, what other equations do we have?
The half-life equations, like, gross.
Okay, what are our half-lives? What is, I guess you tell, what, do you know any of them?
Yeah, I know all of them. The half-life for the 0th order is equal to the concentration, initial concentration over 2K. Then for our first order, it is equal to the natural log of 2 over K, which is kind of cool that it does not have the initial concentration in it. 0.693. And then second order is equal to 1 over K times the concentration.
Yep, so the ln of 2 is a value, it's just 0.693. Okay, so these are all of your half-life formulas. When you're looking, so how to memorize these or something to help memorize them. Whenever you're looking for a straight line plot, your axes here is going to be A over T. So when you look at your half-life, your A has to be up top in relationship to your T. For first order, it's ln of A over T. And so you have your ln function up here that you have to have. And then for your second order, it's 1 over concentration of A over T. And so you have your concentration in the bottom for your half-life. Okay, so I think of it that way, where I have to think of what my axes are for my straight line plots. And so that's how I can tell where my half-life or what kind of half-life formulas I have. Jade, does that help memorize your half-lives a little bit?
Yes, thank you.
Okay, and then any other important formulas? What's related to half-life? What else do we use in terms of first, second, 0th?
Integration rate laws.
We have our integrated rate laws. What do we have for those? You can start with first, second, 0th, whatever you know.
Okay, I guess I'll just go. The 0th order is approximately equal to the final concentration, which is equal to negative KT, which also means that the slope for the graph of the 0th order is going to have a slope of negative KT. And then the negative KT is plus the initial concentration. So we get that nice y equals mx plus b type equation right there. Then for the first order, we approximately have the natural logarithm over the natural logarithm of the final concentration, which is equal to negative KT again, just like our 0th order, but it'll be plus the natural log of our initial concentration. And then finally, the second order integrated rate law is 1 over final concentration is equal to positive KT, not negative, plus 1 over the initial concentration.
Awesome. Okay, so again, if we're looking at our straight line plots, if you have to graph something, you're expecting a 0th order to have a negative slope. Your ln of A should also have a negative slope. But then your second order should have a positive slope. Any questions on this one? Do we feel a little bit better about the exam so far? Yes. Are there any other questions that we have for me? Are there any other equations that we think we should know?
What do you believe that we haven't covered right now on this call that you believe it is imperative that we know for the upcoming exam? Is there any like special sauce that you have for us? Or is there like a special like equation that just like is there anything that you believe you can tell us tonight that would probably be beneficial to us on the exam tomorrow that we have not already covered?
Yeah, so I can just give you just some general tips. Some things that I do for multiple choice, what are these called? Exams in general. Use your exam to your advantage. One thing that it's really important for you to learn, especially early in your college career, is to use your test to your advantage, right? You have homework was like 14, 15 questions. This practice exam was how many questions? 12. Was 12 questions, right? It's probably going to be of similar length. You have 12 to 14 questions that he's going to ask you, all on the same topic, right? Some things are going to overlap. Use that to your advantage. If you're like, and it's multiple choice. It's not like you have to give yourself an answer and you can't pull from anything, right? He is giving you stuff on your exam. Use it. If you don't remember something, look around the exam to see if you can find it, right? That's always super important. I vividly remember taking an exam one time in chemistry and thinking I was reversing something, and then came to a question later in my exam and it cleared it up for me because I read that full question. So trust yourself and use your exam to your full advantage. Also ask yourself, does this make sense? I cannot stress this enough. It is very important to get to an answer and then say, does this make sense to be an answer? Look at your units. Look at the magnitude of the answer that you have. Look at how that changes according to the science that you know up here, right? Make sure your math matches what chemistry you know. Okay, so that's why I asked, if you have temperature increasing, what does your K do? Your K should increase, right? If your K decreased, then that should trigger some red flags. If you are doing a problem and you know it's second order, but your units are coming out to have molarity on top, that should be a red flag because you're saying, no, this isn't correct. I know my molarity should be on the bottom. Okay, so make sure you are constantly looking over your units, constantly looking over just the math that you're doing to make sure that you're setting yourself up for success. And then if you happen to make an error, then you can catch it at the very end because you're asking yourself, was this successful in relaying the chemistry that I know, right? Your math is there to support your chemistry. Make sure that you ask yourself, is the chemistry happening correctly? Those are the two big things I always say. In terms of actual chemistry content, it is hard for like true false questions because he does sometimes pick very one sentence things to ask true false questions about. But again, your true false questions, ask yourself, does this make sense? Can you prove yourself that this is fully true? Or can you find a case in when you can prove it false? Right? Or can you find, if you think it's false, can you find a case in which it would be true? Okay, I think that's always important. If you can look at your question, you think, I think this is false, try and change your true false question to make it true. Try and make it a true statement and say, yes, this has to be false because in order to be true, this would have to change. Okay, so if you look at, if you look at question number 1, we have regardless of the bond breaking always releases energy. Is this going to be a true or false statement?
False. To break a bond, you have to put energy in it.
Right? We're saying this has to be false because I know all bond breakage requires energy. You're allowed to write on your exam. So I would say it's not releases, it requires. And then because I changed that statement, I now know it's false, right? Use that to see, okay, is this true or false? What do I know to be true? Can I make this a true statement? Ask yourself those types of questions. You have more than enough time to do all of these problems, right? It might be a little bit of a race because you're constantly checking yourself, but take the time to check yourself. It does help at the very end to feel confident in the answers you're putting down on your Scantron. Kind of convoluted answer, but that's my secret sauce. Any other questions? Yep. Alrighty, so let's talk about zero with order. If we had a rate law that was zero with order, we would have rate is equal to K. We're just going to call this X to the 0. So what does that actually look like for our rate law?
Just R equals K.
We're just going to say that rate is equal to K. So what should our units of K or units of R be?
Molarity over seconds, correct?
Yep. We can
Yeah.
say molarity over second is usually the typical, but we can say any sort of concentration over time. Okay. So this could be molarity, this could be millimolar, this could be micromolar, this could be seconds, this could be hours, this could be days, right? Just some sort of concentration over some sort of unit time. But right now we can just assume that we're going to be in molarity over second. Okay. So if our units of R are molarity over second, what are our units of K?
Molarity over second.
Also molarity over second, right? There's no concentration that we're multiplying by, so the concentration has to come from that K.
Isn't the rate still negative? Negative K?
Here, no. For your rate law, it's just going to strictly be K. Right, if we were just looking at 2A plus B goes to C, and we said the rate law, it could be A squared. We'll say it's A times B. Right, K is not negative here.
Is this different than the rate law expression?
Yes, yep.
Okay, that's fine.
Yep. Your rate law expression is just relating, is combining like that, the dx over dt, that with the rate law.
Okay, I thought it was saying your rate is equal to K, as in that situation.
Nope, the expression is more the same. The rate is like proportional to negative K over this. Because an expression technically doesn't have an equal sign. But here's a rate law where we're just like using an actual example.
Okay, thanks.
Okay, so then for first order, again, we'll have rate is equal to K. Sorry, I probably X is not the best way to do this. We'll do A. A to the first. What are our units of R?
Is
The
again,
same as 0th order?
sorry.
Is it the same as the 0th order? R?
Yep. So for rate, it's going to be the same. It's still going to be molarity over second. What about our units of K now?
Because we have our concentration in there, that gives us our M. So K is just 1/2. So second to the -1 power.
Right? You can say 1/2 or seconds to the -1, whatever is easier for mathing for you. Yep, but
Why is that?
yep, so your rate here is going to be K times A. So whenever you plug in a question, it would say your rate would be determined by K times, let's say 0.5 molar. So the concentration of A is where you get that M value, or where you get that molarity value. So in order to get your final units to be molarity over seconds, we don't want an extra molarity on top, or we don't want a molarity on the bottom, because then it would cancel out. We just need this to say 1/S.
Okay, thank you.
Right, and then lastly, we have second order. Your rate is Ka squared. What are our units of R?
M over S.
And what are our units of K?
One over S.
1 over
Seconds M.
M times S. Perfect.
M is just molarity, correct?
M is just molarity. Yep,
Yeah.
some sort of concentration.
Concentration.
Right. If we were to plug this in sort of as like a math problem, right? We have rate is equal to K times A squared. We know we're going to have some sort of concentration for A, right? We want rate to be in molarity over second. We don't know what K is in terms of its units, and we know that this will be molarity squared. So we could say molarity over S is equal to K times molarity squared. If you were trying to solve for X or K here, you would divide by molarity squared. And you would get molarity over S times molarity squared. This cancels out, this cancels out. And so you're left with K is equal to 1/M times S. And that's where that comes from. I think those are the big equations that y'all need to know and how like to solve for all of them. And then just knowing your different units for K and stuff is always good, right? Like we saw for question 8 on the practice exam, just by knowing your units, you were able to get to the correct answer. And so if that helps you at least narrow down some choices, that's always helpful in the very end. Because if you do end up having to guess, you definitely increase your chances of guessing correctly. Any other questions? Do we feel better? Thumbs up, thumbs down. In the middle. Okay, I'll take silence as a good thing.
Oh, I have a question.
Yes.
So for osmotic pressure, are there like different ways we should start answering something if it's like isotonic versus hypo or hypertonic? Like how would he approach the problem differently?
Yeah, so he could ask something for like hyper or hypotonic. You would then need to know what hyper and hypotonic mean. And then, right, I think it would be more of like what answer could be hypotonic or what answer could be hypertonic, right? So then you would solve it the same way that we did question 2 and find the isotonic value, and then you would either have to go up or down depending on if you want it to be hypertonic or hypotonic.
Okay, so the equation would stay the same, but you'll just see like where the answer is like greater or less than.
Yep.
So what would be greater, hyper or hypo?
Is this one where I haven't done blood work in a very long time? I believe like if you're hypotonic, then you want to be higher concentration. And then if you're hypertonic, you want to be lower concentration, right? Where it's like higher, means you want to go lower, and then hypo is lower, you want to go higher.
Okay. Does that mean like higher concentration, which means like less water?
Yes.
Okay, thank you.
I think we did miss that equation on our little equation sheet, but it's just the pi v equals nRT, right?
So we can write that right here. We'll finish it. We'll put it right here. IV is equal to nRT. This was osmotic pressure.
Was there an equation sheet to look at for this?
No, we just we were writing down all the important equations we needed to know.
Oh, okay.
Also, R needs to be in atmospheres, right?
Yes, this R is the 0.08206 liters over ATM, which is given.
Will we get like unit conversions on the exam if we need to?
Yeah, if you need a unit conversion, it's given to you.
Okay, thank you.
I believe it's very similar to this guy. And then our units will always stay the same. It will always be some sort of concentration over some sort of time. It might be millimolar over hours. It might be micromolar over seconds, right? It doesn't necessarily always have to be molarity over seconds, but it will always be concentration divided by time.
So does pi always need to be in atmospheres?
Yes. Yep.
Wait, what does pi always have to be?
In atmospheres, it has to be an ATM. So it has to
Okay.
match the R constant given.
Could you explain number 4 on the practice exam?
Yes. So according to the collision theory of chemical reactions, as the temperature increases, the number of collisions per second will increase. Is this true or false?
Yes, it's true.
Does someone want to back her up? Yeah, I agree. This is true. So as we increase temperature, your molecules are gaining energy, right? If we think about, I always relate increasing temperature to boiling water because you start with still water and then it eventually bubbles, right? With enough energy, with enough time, with enough heat, your energy or your water molecules move fast enough to then escape to the gaseous phase and create bubbles. And you can kind of see that with the bubbling happening. So as you increase your temperature, your molecules are moving faster, which means that collisions are happening more frequently, therefore increasing your rate of reaction.
Okay. And collisions, like, I guess if we're using the boiling water example, it shouldn't be confused with like more intermolecular force interactions, since like, I guess they're moving too fast for those to stick.
Yes. So as you, right, that boils down again to them gaining energy. As they're gaining energy, they are decreasing their intermolecular forces with each other. But they can cause collisions. And if those collisions are at the right orientation, at the right energy and whatever, then that's when you can form a bond. And then if that energy is high enough, and then that bond that forms is low enough energy, then you'll fall back down and that's where the reaction stops.
Okay, but like for the more collisions per second, it'll get, I guess, more chaotic, so there's less chance of a correct orientation?
There's not they're more chaotic, and so like the frequency of collisions are happening. So since the frequency is going up, then the frequency of correct orientations is also going up.
Oh, okay. It's not like it's lessening, it's still increasing.
It's still increasing, yes.
Okay, so for also like for bond breaking and forming, is it like the same thing where if there's more kinetic energy, you need to break the bond so the molecules go faster and there's less force attraction in between them?
I think yes, if I'm understanding your question correctly. Here for bond breaking and bond forming, mostly you just need to know that bond breakage requires energy and all bond formation releases energy.
Okay.
Mhm.
Thank you.
Any other questions, ladies and gentlemen?
I didn't see for the practice exam, I didn't see the like key posted. Like it says on my Canvas that there's a key, but the key doesn't have the answers, or am I like missing something?
Let me check.
If you pull it up on an iPad, it won't show the answers. It works if you pull it up on a computer though. The answers are like highlighted when you pull them up on the computer.
Oh, okay. I don't
Yeah,
have a
if-
computer. I
yeah,
just have an iPad.
If you download it, I don't know. We'll try. We'll just go to Canvas. This is on an iPad. Let's see what happens. Okay, so if you download it to your iPad, it should pop up.
Okay, thank you.
Will this recording be posted on Canvas?
Yes, I'm gonna brush my teeth and get ready for bed, and then by that point, the Zoom should hopefully be done, and I can upload it real quick.
Okay, thank you.
Anything else? Feel okay? Okay, well, if there's nothing else, good luck tomorrow. I will be there with your exams, hopefully around 12:20. If you were at my review session yesterday, I do have group meeting in the morning, so I can respond to emails probably after 10:30, maybe 11, depending on how long we go. So if you send me an email before then, just give me until like 11 to respond to it. And I'm presenting, so rough. But if you have any questions, please email me and let me know, and I will respond to them before noon, hopefully. If there's nothing else.
Quick
stop.
question.
Yeah, go ahead.
If you're monitoring the exam, can you ask him to update the time more frequently? Like time left?
Yes, so he doesn't like to interrupt y'all. So
Like just on the board, yeah.
yeah, he tries to do it every like 10 minutes or so. He'll up
Oh,
her
okay.
where it's like 10 minutes left or 20 minutes left.
Okay.
I can ask him if he can make like a halfway comment.
Okay, thank you.
And then if you have any friends, we're gonna make an announcement tomorrow, but please enter in your version correctly on your bubble sheet this time. That'll save me an hour of my time. Because then I don't have to look at all of your exams and fill it in myself. But please put in your version tomorrow. That will save a lot.
So like version A, B, C, D.
Yes, if you're in 12 o'clock, you will have A or B, I believe. And then if you're in 12:40, and then if you're in 3, then you'll have C or D, I think, like last time. Unless he tries to switch it up, but should be at the very front of your exam. It should say exam 2, A, B, C, or D.
If I remember correctly, did he say last time you don't have to worry about it because it's color coded?
Yes, but he did not know how the exams were graded. And
Ah, gotcha.
I did not know how the exams were graded. So once I got there and I'm like, then I had to, if I want to just talk about my struggles real quick, I had to click into every one of y'all's exams and look at what color it was and then manually click if it was A, B, C, or D. There are 477 of you. So that was a lot. So they will still be color coded, but it's just nicer on the Scantron if I know what it is.
I also have a question about scantrons.
Yes.
So I have this. Yeah, it's really hard to see. So it's
I
like a
see
light blue color, and
Yep.
then I have the dark blue color one.
Okay.
Which one do y'all use?
So we have the one from Gradescope directly, so it should be attached to your exam, I believe.
Okay.
Yeah, so you don't need to provide your own Scantron. Yes.
Thank you so much. This was really helpful.
Awesome. Anything?
Thank you.
Oh, happy to
Good
help.
luck on your presentation.
Thank you. I have to go finish one slide and then I think I'm going to bed. So alrighty. Good night, y'all. I'll see you
Thank
tomorrow.
you. Good night.
Stop studying. Go to bed.
Hope you, if you have any exams, that you do well on them, Allison.
Thank you. I appreciate it. I hope y'all do well as well.
Thank you.
Thank you. Good night.